recorded last time. So let's have a look. We're back. And let's have a look. Let's stop this. So what are people saying? People are saying, oh, mainly D, but a bit of C. So let's have a look at this. So what I do is I visualize it and I say, well, here's my mass and here's my 3 kilograms and it's going in a negative direction. Okay, so it's minus 3 meters per second. And momentum is equal to mass times velocity. So my momentum is equal to my mass. And my mass is, did I put that down right? 3 and 4. Yeah, okay, thanks. It's not like me to put down the same number twice, although I do it sometimes. So P is equal to minus 12. What was it going to be? Kilogram is mass, meters per second. So it's D is the right answer. So the sign does matter. You know, the sign does matter. So, following on from that, what is the momentum of a 5 kilogram block that has a velocity of that? So can you do that one for me, please? Okay. So we're back, and let's have a look and see what people said. Mainly C. Let's have a look at this. So I'm going to have my, again, my visualization is important. I'm going to have my 5 kilogram mass, and I don't know which direction this is. I just do an arrow, and I go, this is going to be 3I plus 2J minus 4K, and that's going to be meters per second. So I go, well, P is equal to M times V. So let's have a look. This is going to equal, it's going to be my M, which is 5, times my V, which is 3I plus 2J minus 4K. And this, of course, is not a dot product because I don't have a dot there. It's not a vector times a vector. And so in this case, I can just multiply these guys together linearly. And so I go 15I plus 10J minus 20K. And then I go, that's going to be kilograms, meters per second. Put it in a nice box so we can find it. And I look on this thing, and is it there? I guess it's here, isn't it? It's going to be C. Yeah. And just a word to the wise. Most common mistakes on something like this is people multiply the first two numbers together, so they'll go 15I, and then they kind of forget. So then I get 2J minus 4K, or they'll do the first two coefficients but forget the third. So, you know, with experience you get to the stage where you know what to check for. So I know I've got to check for all three. And again, just as your coach, I've got to tell you that the more you write down, the fewer of those slips you'll make. If you're writing things down, you'll catch them. And then, of course, the other thing is units. Units are really important. I don't want to miss out on units. Just because I wrote IJK does not relieve me. IJK is just dimensionless vectors. The whole thing still needs units at the end. Cool. Okay, let's do something let's derive something. Part of physics and engineering is you derive something and then you learn from the derivation. So if we remember that acceleration is the rate of change of velocity with time, I can say, well, if P is equal to mv, then if I differentiate both sides, I get dp by dt is equal to dmv by dt. And of course, you take out your constants. Mass is not going to change during this thing, which is m dv by dt. And if I think back about my kinematics, dv by dt is acceleration. Oh, well, hold on. I thought F net is equal to ma. And yeah, that means that my F net, or the sum of my forces, is equal to dp by dt. That's not obvious. Interesting little quirk is that Newton never spoke in terms of acceleration. He didn't formulate that idea. He spoke in terms of dp by dt. So he invented calculus, and then he thought about things in terms of the rate of change of momentum. So quite what we find quite sophisticated thinking, quite complicated thinking. And it's because later on somebody came along and said, you know, why do we call this acceleration? And then they kind of developed that terminology. We're really fortunate in the, because people wrote things in their lab books, and because they didn't staple things in, but they stuck them in with tape on all four sides, we still have their lab books, and we can look back and see them struggling to describe what they were doing. And it's language. It's like, you can see Newton, when he's going through this, just struggling for the word, because the word is not really there. And then he coins a term. And we know that term because we grew up with it. But it was invented by him. It's like the invention of technical language. And without the word, it's very hard to put things and ideas. But with the word, it's easy. And we take it as obvious. Acceleration is obvious. You can see acceleration. A car speeds up, it accelerates. Boom. But that word had to be developed. And so to some extent, the struggles that we have at the moment in science is often the fact that we don't have the vocabulary to discuss what's going on. We don't have the way of thinking. So this is my own little conceit, is there's the research people doing stuff, and then behind them are a whole bunch of teachers saying, this would be a good thing to term this way, or let's teach it that way, or no, let's talk about it from that point of view, which makes it more accessible to people. Because research itself is very inaccessible. It's very hard to follow a research paper, even though it's just science. And it's because of the language they use and because of some of the special skills that they use. So a textbook is different from a research paper because it's been filtered through a whole bunch of teachers to make it more accessible. So everything in your book is there because it makes life easier. It makes you more powerful, and it makes life easier for you. If you're not doing it the way it's in the book, then you've got to say why, because it's like, this is the easiest way that people have found. So think of it as not being your test, but being your friend. It makes you much more powerful by following those techniques. So let's have a look at this. An 18 Newton force is applied to a particle. The force acts in the positive x direction. So we have the positive x direction, and this is 18 newtons. The particle is initially at rest, so VI is equal to 0 meters per second. What is the momentum of the particle? T equals 6 seconds, so PF at delta T. Let's say delta T equals 6 seconds. It's the time, but let's start the clock off at 0. This says 6. That says 6. So, looking at this, and looking at that, and not getting distracted by kinematics, can you do that for me, please?
Does that say PF?
Does what bit say PF?
Right above delta T?
Yep, P final. That's what you want. P final. It says, what is the momentum of the particle at T equals 6 seconds? I'm going to stop that. So let's do this one together because it's harder than I thought it was going to be. So let's go on. So, okay. There's a couple of ways you can approach this. One way is the kinematic way, where you turn around and say, well, okay, I want the final momentum. And the final momentum is equal to the mass times the final velocity. And the final velocity, well, VF equals VI plus A delta T. And so I can say, well, hold on, VF is equal to VI. VI was 0 plus A, and delta T was 6. So I need to find my acceleration. And I know that my acceleration is equal to my acceleration. My acceleration is given by F is equal to ma. Oh yeah, stock. We can't do it because we don't have the mass. I wonder if it'll cancel out. So I say F is equal, so I say 18 is equal to the mass times A. So A is equal to the 18 over the mass. Okay, so then I say, well, can I get anywhere further with this? And I can say, well, then that means that, means that my P final is equal to m times my V final. So my P final is equal to m times my, let's have a look. It's going to be A, which is 18 over m, that's my A, times 6.
And then cancel out the M's.
So P final is equal to 18 times 6, 60, 48, 108. Man, that was hard work. What are the units going to be? I'm a professional, sorry. So that's the way you can do it doing kinematics. Is there another way? And there is. And I want to show you it, although I'm cheating because I'm going to introduce a bit that you've not got to yet. So you've got that down?
Oh no.
Okay. Okay, we're back, and let's first of all stop this, and let's go along. I'm going to erase, if I have an eraser. Oh, brilliant. Let's see what I can do. I can do that. I can do that. I can do that. Because, as a gentleman just pointed out to me, and I'm very grateful, there's also, we could just use the equation that's given with a bit of insight. And, yeah, which is, so, if in doubt, use the equation that we just talked about. So, so let's have a look at this. So pointer, and so we say, well, I suspect this has something to do with this equation. So here's my mass, and here's my force, and then this was 0 meters per second, and then here's my mass, and this is at t is equal to 6 seconds, and here's my P final. And so what you say is, well, the sum of the forces is equal to dp by dt. And let's just get a bit, averaging. Well, that's like delta P by delta T. And let's just go a bit and express that a bit more. That's P final minus P initial over delta T. And so I can say, well, now let's look at our diagram. We say plus 18, because it's pointing in the positive direction, is equal to P final, that's what I want, minus, now, is the conceptual bit, if P initial equals mV initial, and my V initial is 0, my P initial equals 0, over delta T, started, and then 6 seconds later, that's going to be 6. Oh! P final is equal to plus 18 times 6, which equals plus 18 times 6, which equals 6 8s, 48, 108. So which do you prefer? I think this second method is a bit more straightforward. Cool. Very, very good. Okay. So, very good. Thank you ever so much for that. Let's make it look a bit harder, but it's the same thing. A 3I plus 2J plus 4K Newton force is applied to a particle. The particle has initial momentum of that. What is the momentum of the particle? It's equals 5 seconds. So can you ever go at that one for me, please? Okay, we're back. Let's have a look at this. So let's stop that and let's see what people are saying. People are saying C. So let's have a look about this. So what I've done is I've done my diagram, and basically, it's not please. So I did my diagram, and basically I have my mass, and I put in my force, and I put in my momentum, my initial momentum. No idea what the directions, I just represent them by arrows. And then I put my time interval, which is 5 seconds, and then my P final is what I want. I always put down my P, what I want, because sometimes you get lost and you're trying to find something that you don't have. And what was that thing again? What was it? The force is equal to, what was it? dP by dt? And we said, well, on average, that means it's the delta P by delta T. And that means it's our P final minus our P initial over our delta T. So then I can say, well, let's just rearrange this. And I say, well, okay, this equals, let's do it, P final over delta T minus P initial over delta T. So then I say, well, I'm going to call it F net, doesn't matter. F net, take this to the other side, plus P initial over delta T is equal to P final over delta T. So that means my P final, which is what I want, is equal to F net plus P initial over delta T all times delta T. And this equals, man, I'm running out of space, aren't I? This equals F net times delta T plus P initial.
Seems more complicated.
I'm just writing down my steps. So then I say, well, F net, I know F net. I want F net times delta T. Delta T is 5. So this is 15 rather than 3. 3 times 5 is 15. 2 times 5 is 10. 4 times 5 is 20. And then plus PI. PI I was given. PI is 1 minus 6 plus 7, which equals 16. I'm adding them together. That says to add. So I'm adding them together. So that's 16 plus 4 plus 27. So I have 16I plus 4J plus 27K. And it's going to be in kilogram meters per second. And I think that's my answer. Yes?
You could have skipped a step there when you're writing out your steps, and you just multiply both sides by delta T to begin with.
Cool. Fair enough. Okay.
It's made more complicated than you needed to.
Well, either way, it's just algebra. As long as find your way, but write it down. Okay. Don't do it in your head. Find your way, but write it down. Okay. On that, looks hard, but it's the same principle, isn't it? Okay. We've just had, if you like, the force dP by dt relationship. Now we're going to do an impulse momentum relationship. So let's just think about this. We just had our force F net is equal to dP by dt. Okay? So compare and contrast that with this thing called impulse is equal to my change in momentum. They are similar enough that you might get them confused. They are different enough that they're not the same thing. So whenever you get something like this, put it down side by side and kind of live with the two of them for a while. Because the last thing you want to be doing is trying to solve the first type of problem using the second equation and the second type of problem using the first equation. So whenever things are similar enough that you need to compare and contrast them, just put them on a paper side by side, and just compare and contrast them, because otherwise people get confused. So what is this thing called impulse? If I apply a force to an object, it will accelerate. Yeah? If I net force, if I apply a force to that object, it will accelerate. Acceleration is a change of speed and or a change of direction. My change of speed and or my change of direction really depends on how long I apply that acceleration for, which means how long I apply that force for. So really we have to take into account duration. Duration matters when we're pushing and pulling things. So this is a way of taking into account the duration. That triple equal sign means we define. We define impulse is equal to the applied force multiplied by the duration. Now, if the force is changing in time, I need some way to take into account the changing force in time. And so, colloquially or simply, I can say my impulse is defined as my force times my time, and that's great for a constant force. But if it's not a constant force, I need to take into account this more generic term, which is it's the integral, the sum of all the little changing forces multiplied by the little amount of time. Okay, so I have this thing called impulse. By the way, I'm going to warn you, in a little while we're going to be using I to mean moment of inertia. So again, we're running out of symbols. So I tend to use IMP for impulse. You can do it either way. I think the book uses I. It's contextual, you know, but for my own writing, I prefer IMP. Got a question or comment?
Yeah, does this also mean that if I is delta P, so is that like the net force is equal to I over delta T?
So I is delta P. Impulse equals my change in momentum. We're going to get to that, yes. That's where we're going. We're going to prove it. Yeah, you're ahead of me. Good. So, okay, I'd invent this thing called impulse. Impulse. It is the force times the duration. And then we say, okay, well, if we remember that the sum of the forces or the net force is equal to dP by dt, we can substitute in for that force. And we say I is equal to the integral dP by dt multiplied by, well, integrated with respect to time. Well, that gives me my impulse is equal to my change in momentum. So that's where that comes from. So that's where this second expression comes from. Again, it's similar enough to the first expression that we did just a few minutes. These two are similar enough, well, these two are similar enough that you've got to compare and contrast them. I see people get them backwards all the time. So this is impulse momentum relationship or impulse momentum theorem. If you have an impulse that is a force times a time, then you have a change in momentum. It's got to be. You can't really apply a force for no time, otherwise who cares? So whenever you apply a force, you're going to get a change in momentum. Most forces are not nice and constant. If I hit a bat or kick a football or something, I start off barely touching, so my force is very little, and then I get a stronger force and a stronger force and a stronger force until I'm maximally engaged with the football, and then the football starts to elastically spring away from me, so there's less contact and less contact and less contact and less contact until finally I break contact. So my force-time relationship is some convoluted mathematical expression. And I'd like to be able to work with that as a practical basis. And what I recognize is, oh, this is the area under a force versus delta t, or force versus time graph. So if I have my force versus the time, and I just take the area under it, that's my impulse, which is kind of cool. And that opens up another possibility that I can have a complicated interaction, but I can define a time duration and say, well, what is the average force? Well, it's hard to look at this first graph and say what the average force is. But if I say, well, the average force times the duration has the same area as the actual force in time, if these two areas are the same, then it makes it a lot easier to find my average force. So it's kind of interesting. We say impulse is the area under a force versus time graph. Impulse has units of Newton seconds. And we say impulse is equal to the time average force times the interaction time. Let's go back up here for a second. If impulse is equal to Newton seconds, and that equals my change in momentum, the change doesn't matter. Momentum is in kilogram meters per second. They numerically have to equal each other. When I say I is equal to delta P, they numerically have to equal each other. But they also have to dimensionally equal each other, which means their units on a fundamental basis have to be the same thing. And so if I look, well, newtons and seconds don't, at first glance, seem to match kilogram meters per second. But if we think back, a newton is Well, MA. It's kilogram meter per second squared, because kilograms is M and meter per second squared is A. So there's my Newton, and my Newton seconds is equal to a kilogram meter per second squared times a second, which equals kilogram meters per second, which is mass times velocity, which is that. So these guys are the same. They're just different units. So they look and they're written as different units, but they're dimensionally the same. And that's one of the disadvantages of having named units. When you name something
So
after
small s is the unit.
small s is seconds.
Okay.
Yeah. So
Seconds.
so so the dimensions are important. Did you have a comment or a question? Okay, cool. So so watch out for that, and it's just one of the disadvantages in that we name units after famous people. By the way, I don't mind. I know it's going to be confusing. I don't mind if you put down kilogram meters per second when it's impulse. Yeah, it's like, all right, fair enough. I don't mind if you put down Newton seconds when you mean changing momentum. It'll happen occasionally in an equation. You'll get the wrong units. You're putting down units, and they are dimensionally correct. So, you know, in time you'll get so that you don't make those slips. But in the meantime, make sure you're putting down a unit and recognize the fact that a Newton second is the same as a kilogram meter per second. Okay? Particle is acted on by a force of 12 newtons that acts in a negative direction. Let's say the negative x direction. The force acts for 5 seconds. What is the impulse of that? Okay. So let's stop it there, if I can. And let's see what people are saying. Most people are saying D. Let's have a look at that. Whoops. Sorry, I'm back at the beginning again. So here's my visualization. I have my mass, and it says 12 newtons that acts in a negative direction. So I put my negative, call it minus 12. My time is saying 5 seconds. So what is the impulse of this force? An impulse is equal to, it's going to be the force, if the force is constant, times the duration of the force. So my impulse is equal, and the direction of the force matters, so it's minus 12 on a number line. I'll call it positive and negative. And then this is 5. So my impulse is equal to minus 60, and it's going to be Newton seconds, which is that by there. Cool. And so let's make it look a bit more, again, it's just the same thing, it's just got IJKs in it, just makes it more powerful. I can do 3-dimensional stuff now, but it's mathematically, it's just sums. So can you ever go at that one, please? So we're back. Let's stop this somewhere. Stop this and see what everybody's saying. Yeah, everybody's saying A. And what's going on here? So this is one of these things where it looks deceptive. It looks like, man, it's IJK again, but it's just checking on your definition. So my impulse is equal to my force, if it's a constant force, times my duration. So my impulse is equal to, my force is 3I plus 2J plus 4K times my duration, and my duration is 4 seconds. So my impulse is equal to 3 4s are 12I plus 2 4s are 8J plus 4 4s are 16K. And this would be Newton seconds. Little hats on everything, and we're in business. So not bad at all. Cool. Stationary particle is acted on by a force of 7 newtons that acts in a negative x direction. Force acts for 3 seconds. What is the particle's momentum after this action? Stationary particle. Can you have a go at that, please? Just let me do this. Give me a sec. Hold on. So let's stop there. And let's look and see what people are doing. So that was me doing B, just to check to see that thing worked. I swear. So people are saying E. So let's have a quick look at this. So stationary particle. So VI equals 0 meters per second. Is actually done by a force 7 newtons that acts in a negative direction. Let's imagine it in the x direction. So that's going to be minus 7 newtons. Force acts for 3 seconds, so delta t is equal to 3 seconds. And what is the particle's momentum after this? So I want P final. So I say, oh, you know what? Impulse is equal to my change in momentum, which equals P final minus P initial. And I know that my force times my duration is equal to, I want my particle's momentum, I want my P final, minus my MVI. That's what my P initial is. So I can say, oh, hold on then. Let's just say my force, which is minus 7, I look at my diagram, and I say that's 3, and that equals P final minus, and oh, stationary particle means 0 for that. And the units are going to be momentum, kilogram meters per second. So it's going to be minus 21. It's going to be E. Very good. Okay. This next little bit, where am I going? Yes, I'm going to do this next little bit, and then we're going to take just a brief break. So this next little bit is basically, in fact, what I'm going to do, well, I'll do it now. If I look at a 3-dimensional problem, well, actually, 2-dimensional in this case. So I have 2 particles and they collide. Well, according to Newton's third law, then the force of one particle on the other, the force of 2 on 1 is the same as the force of 1 on 2. Just opposite directions. We agree on that. And the time of interaction, my delta t for the first force is equal to this delta t for the second force, because I can't push you without you pushing me. And I push you for as long as you push me, and you push me for as long as I push you. So the times are going to be the same. And so my impulse of this guy is going to be the same as the impulse of that guy, which means my change of momentum for this guy is going to be the same as my change of momentum for that guy. And so that means, oh, hold on. If the change of momentums are the same, I can go through this. Now I need to do some math. So I say, consider 2 particle systems. The force of the one is equal to the force of the other, just opposite direction. And force equals the time rate of change of momentum. So the time rate of change of momentum for particle A is the same as the time rate of change for particle B. And these 2 guys are equal to each other. So then if I look in this, I go, well, if I say these 2 forces are equal and opposite to each other, then that means I get that, which means my change in momentum of that guy plus my change in momentum of that guy equals my change in momentum for the whole thing, which equals 0, because that equals 0. I didn't explain that really well, but just go through the math and it comes out. So the take-home message is that my delta P in a collision equals 0. There's no change. Or if you like, P initial equals P final. That's why momentum is so important, because it's the one thing that links all collisions before the collision with after collision. It's like the magic thing that's constant. We always look for consistency because we like equations. It's the one thing that's constant throughout a collision. And the way you remember it is you can always rely upon your mom, you know? Momentum is always the same. You go home, it's the same. So other things like kinetic energy are not always the same. And we'll talk about that in the next section when we come to collisions. So let's pause there and we'll do a... So we're back. So let's talk about collisions. There are two basic types of collisions. There's one where kinetic energy is conserved, and there's another type when kinetic energy is not conserved. And kinetic energy is in a moving object, so there is some kinetic energy to begin with, and you have less kinetic energy after the collision if you can feel it in terms of heat, or you can hear it in terms of a crash. That energy that's coming to you has been paid for by the kinetic energy inside the system to begin with. So fender benders or and the like are stereotypically kinetic energy is not conserved. If you are getting energy out of the system in terms of heat or light or sound, then kinetic energy is not conserved. There are some collisions where that doesn't occur. In some ways, you could turn around and say, well, you know, when a comet swings around the sun, it is colliding with the sun. There's a force interaction taking place. When electrons push against each other, there's a force interaction. It comes back to what is a collision? Is a collision touching? Well, nothing ever touches anything. There's always electrostatic forces in between. So sometimes our definition of a collision needs to be broadened a little bit. So gas molecules hitting each other, that tends to be kinetic energy is conserved, and the like. Question or comment at the back?
With the one with the billiard balls, for that one, you said that the kinetic energy is conserved, but when the balls hit each other, isn't there sound?
So there's, you got to forgive a little bit in order to make this thing somewhat visual and memorable. We use examples that somewhat indicate, but they're not perfectly true. So we'll get to those three in a minute. Okay? But you're right. So divide the world up into situations when kinetic energy is conserved and situations where kinetic energy is not conserved. Remember, at all times, momentum is always conserved. So that would lead to two problems. Kinetic energy is conserved and momentum is conserved, and other situations where kinetic energy is not conserved, but momentum is. But then we go and divide the situation where kinetic energy is not conserved into a little subset. There's a special subset of that. So we end up with three types of collision. We have the so-called inelastic collision. Sorry, I got to find my pen. Where's my pen gone? Let me get to my pen. So we have the so-called inelastic collision. There's two flavors to this. There's the inelastic, which is basically a fender bender, two cars hitting each other and then, you know, scurrying off. There's a lot of heat and sound and fury. Kinetic energy is not conserved. So there's our inelastic collision. And then there's a special case of this where not only do these things collide, but they become enmeshed. Two particles become one. And kinetic energy is again not conserved. Momentum again is. But the difference between these two is you know something about the second case. You know that the two masses stick together. So you know they have the same velocity after the collision. So this is a perfectly inelastic collision. And these two should be contrasted with... An example of the perfectly inelastic collision could be a rugby tackle, or I guess in American football, are you allowed to grab hold of a player and pull them to the ground? Or can you only... Thank you. Can you only... Thank you. No, thank you. Thank you. No, thank you. Can you only... or can you... I've completely lost my train of thought now. In rugby, in American football, can you only push people, or can you grab them and throw them to the ground?
You can grab and throw them.
So, okay, that's what we're talking about. The grabbing and throwing to the ground with you holding on to them, okay? A mud pie, if I throw a mud pie, it tends to stick to the, not that I know, but it tends to stick to the face. Tomatoes will stick on people as opposed to bouncing off. So, that is the elastic collision. In an elastic collision, not only is momentum conserved, but also kinetic energy is conserved. When I was a student, to show just how kind of naive I was as a student, I remember telling my buddy that I hoped we got an elastic collision. And my buddy, being a bit more mature than I was, said, "Why would you want an elastic collision as opposed to the other two?" And I said, "Oh, because with an elastic collision, there's two equations, so I got twice the chance of getting it right." And of course, as a teacher, I know that with two equations, I'm going to give you two unknowns, and so you're going to need both of them. So it's inherently a harder question. It need not be as hard as it would be if you did truly try to use conservation of momentum and conservation of kinetic energy. If you do try to solve an elastic question using conservation of kinetic energy, good luck, because it is just a tedious bear. And along came a teacher. I'm sure this was a teacher who said, "You know, if we look at the way the velocities change throughout an elastic collision, then we can use that as our second equation." So although in an elastic collision our momentum is conserved and our kinetic energy is conserved, we morph our conservation of kinetic energy into this equation here, which makes life much easier. Okay? And this is saying the difference in the velocities before the collision is equal to the negative of the difference in the velocities after the collision. Now, to my mind, most of the time equations are easier than words. But in this particular example, I prefer the words to the equation. So the difference in the velocities before the collision is equal to the negative of the difference in the velocities after the collision. So 3 examples. Let's do one. Can you do that one for me, please? This says a 7 kilogram particle with a velocity of 4 meters per second positive collides inelastically with a 2 kilogram particle that has a velocity of minus 3 meters per second. After the collision, the 7 kilogram particle has a velocity of that. What is the velocity of the 2 kilogram particle? So this is going to help you before I move away. So this is the before picture. And this is the after picture, and this is a 7, and that's a 7, and this is a 2, and that's a 2, and I'm going to say this is plus 4, and minus 3, and then the velocity of the 2 kilogram particle. The 7 kilogram particle has a velocity of plus 2, and then I want that as V. So I'll put this on pause. So just a few more seconds. Let's get number 20. I want to see number 20. Come on, come on. Hey, there's number 20. Good. So let's stop. Let's see what people say. Mainly C. Let's have a look at this. So my principle. Let's step through this. P initial equals P final. So M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. So it's not the momentum of an individual particle, it's the momentum of the system before and the system after. I'll look at my diagram now, and I go 7 times plus 4 plus 2 times minus 3 is equal to 7 times plus 2 plus 2 times v. I make no attempt to guess the sign of v. The answer will tell me which direction this 2 kilogram particle is going. And then I just work now my objective is just don't make a math slip. So I'm going to say plus 28 added to minus 6 is equal to plus 14 added to 2v. So I'm going to 2v is equal to 28 added to minus 6, taking this to the other side, added to minus 14. So then I go 2v is equal to 28, that brings me down to 22, and that brings me down to 12, 8. So v is equal to 8 over 2, which equals 4 meters per second. It's positive 4 meters per second. So is that the right answer?
Yeah.
Positive 4 meters per second. Question? Come on.
Will you tell us what type of collision it is usually?
No, absolutely not.
No?
So then, okay, what are the other scenarios? How would I change this question? If I told you that the two masses stick together after the collision, I just told you it was perfectly inelastic. And by the way, I couldn't tell you then that this 2 meters at the end I couldn't include. So that's one way. If it was elastic, then I would have to somehow tell you it's elastic. And in truth, I would have to tell you it's elastic. I can't think of a scenario where I, by implication, say it's elastic. I suppose I could say kinetic energy is conserved, but then I'm telling you what elastic means. So I'll make it relatively clear, but it's from the wording. Yeah. Cool. Okay. Speaking of perfectly inelastic, 3 kilogram particle with a velocity of 3 meters per second collides perfectly inelastically with a 2 kilogram particle that has a velocity of minus 4 meters per second. What's the velocity of the combined particle after collision? And let's do this I'm running out of time, so yeah, do this real quick. Turn it on. And again, I'll just do the diagrams are everything. So 3 plus 3. I'm going to pause that there. Okay, we're back. So let's pause this thing here. And let's see what most people are saying. Most people are saying A. A little bit of B, a little bit of C, but most people are saying A. So let's see how that works out. So I took the liberty of, I have a 3 kilogram block with a plus 3 meters per second. Bad teaching there because I'm using the same numerical value for both of them. That can be confusing. And then I have my 2 kilogram with minus 4. And then what I do over here, which is why I paused there, is I like to do this. It's a 3 plus a 2. And I'm just going to call that V. So there's the little trick. My principal, P initial equals P final. And then I go M1, V1 initial plus M2, V2 initial is equal to M1 plus M2 times V final. It's the same equation. I don't learn this. It's just applying my original momentum equation to this particular scenario. Looking at my diagram, I have those two masses. I don't add them in my head initially. I'm going to put the numbers down because I want to be able to check this. So I go 3 times plus 3. Notice masses are just positive. Velocities have signs in front because it's a vector. Plus 2 times minus 4 is equal to, and I'm going to go 3 plus 2 because I want to be sure when I check it that I did remember to add those two guys together, times V final. So I'm going to go plus 9 added to minus 8 is equal to 5v final. So plus 1 is equal to 5v final. So v final is equal to plus 1 over 5, which equals plus 0.2 meters per second. Oh, no signs on this. Yeah, I should really have a sign here, but so mainly A. Agreed? Question or comment?
So on the test, you would say that it's perfectly inelastic.
So I might, or I might say they stick together. You know, what I'm saying is I have to tell you one way or another. I have to give you information that would enable a reasonable student to be able to figure out what's going on.
So stick together, it's perfectly inelastic.
If they stick together, it's perfectly inelastic. That's the thing. Okay. 2 kilogram particle with a velocity of plus 5 meters per second collides elastically with a 4 kilogram particle. I'm going to do this one because I'm running out of time and it's an elastic one, so let's just do it. So I have a 2 kilogram particle and it has a velocity of plus 5 meters per second. Collides elastically with a 4 kilogram particle with a velocity of minus 3 meters per second. And that goes to the 2 kilogram particle and the 4 kilogram particle. They don't stick together. And I don't know what either one is, so I'm going to call that one V1 and that one V2. Might as well leave them both in the positive direction. There's no point in guessing about that direction. And then the next thing I do, and believe me, I've learned this the hard way, is immediately I try to figure out which one of these do I want. And it says, what is the velocity of the 2 kilogram particle? So I'm circling that V1 because I don't want to find V2 and think that's my answer. So from the get-go, I say, what do I want? Then I say my P initial equals my P final. So I'm going to say M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Frankly, in a test I might skip that step, but I'm been a bit risky if I do that. So 2 times plus 5 added to minus 4 times minus 3 is equal to 2V1 plus 4V2. So let's just do one more little step. So that's going to be plus 10 added to minus 12 is equal to 2V1 plus 4V2. So that's going to be minus 2 equals 2V1 plus 4V2. Agreed? Just rearranged. Next bit, I'm going to change colour of my pen so we see this is a separate little thought. I'm going to go to green. So rather than using, and try it, I suggest you go home and try it and just see what a disaster it is trying to use kinetic energy before equals kinetic energy afterwards. It's horrible. So I say, oh, but I know my difference in my velocities before, V1 final minus V2, before difference in my velocities, V2 initial minus V1 initial is equal to the minus of V2 final minus V1 final. Actually, I want to stop that because yeah, I'm doing it. I'm being overly careful. It probably makes no difference, but I just want to be. Yeah, let's do that again. So green. So let's just turn around and say, stop. Let's just turn around and say, ooh. Let's just turn around and say V V1 initial minus V2 initial is equal to the minus of V1 final minus V2 final. I'm rushing now, so I might make a mistake. So I'll look at my thing, and I go plus 5 minus 3 is equal to the minus of V1 minus V2. So then I go plus 5 minus minus 3 is 8 is equal to, let's work out these signs. It's going to be V2 minus V1. So I have two equations. What I need to do is rearrange. I'm trying to find V1. So in this one, isolate V2. Always isolate the thing you don't want in your first equation. So V2 equals 8 plus V1, and then substitute back in there. So I go minus 2 is equal to 2V1 plus 4, and it's going to be 8 plus V1, which equals 2V1 plus 3 eighths, 24, 4 eighths to 32 plus 8V1. So then I take that to the other side, minus 34 is equal to 10V1. So V1 is equal to minus 3.4 meters per second, which is not there.
This is 4v1, not 8v1.
Is it 4v1?
Yes, it's 4 outside of parentheses.
5 minus, that's 8. So this is,
Yeah, it's 4.
I subbed wrong, 4, there's a 4 from there.
Then on the other side of the green thing, it's 2v1 plus 32 plus 4v1. It's not 8v1.
Oh, let me pause. So we're back, yeah, and I'm sorry I'm rushing, so I made this mistake, and somebody just pointed out to me, thank you ever so much. So this is, 2v1 and then 4v2. If I substitute in, that's going to be 4 eighths to 32 plus 4v1. So I take this to the other side, and I'm going to get, what's that going to be? 6. Yep. 4v1 plus 2v1 is 6v1. So v1 equals 34 over 6, which equals minus 5 point, what's that going to be? 66?
5.66
meters per second. Sorry, it rushed, and I'm going to turn it off. So just, go step by step.